think so. Yeah.
First session is always fun. Getting sweaty please by the second one. Okay, you're good to start.
Go ahead.
Yeah, go ahead.
Okay, hello. Let's get started. Right. So, um, I love the idea of this conference. It's about academia and industry needs to talk. So, a bit about me. Um, I'm working for Facebook now on static program analysis, but I came from academia. I was a professor for like 20 years or 22 years before joining Facebook. And so, what I'm going to do in this talk is I'm going to get to the Facebook part, deploying program analysis, but I'm going to go back a bit before that to some of the academic work we did, and I'm going to talk about some of the sort of weird and wonderful things we've learned trying to take some academic research and apply it in this industrial setting. So let's go back in time a little bit. So we're working on program verification or static analysis. Um, we had a paper in the Computer-Aided Verification Conference in 2008, the CAV conference, where what we were trying to do is make a program analysis which takes in a program and tries to prove that it has pointer safety or memory safety. So there are no null pointer dereferences, no memory leaks, things like that. In order to do this, you had to do something called a shape analysis. So we wrote this paper, and the largest programs we were handling were around 10,000 lines of code. This was C code. Um, we found some bugs in the code, and then when we fixed the bugs, our program analysis confirmed that there were no bugs left, right? So it verified the code. Um, I thought this was this. I love this. I thought this is awesome, right? So a bit about my background. I came from denotational semantics, then I did logics of programs, and somehow I got dragged into doing static analysis, and finally I'm doing static analysis in industry. Well, this was at the leading edge of academic research in static analysis and program verification of around 2008. So at that time, program verification was going through a renaissance because of SLAM and Astray and certain tools which you would call verification-oriented abstract interpreters. And so a great thing about this work is that, right, so we found a bunch of bugs. Two of our collaborators on this paper, Burdine and Cook, were working at Microsoft at the time. These bugs were missed by the celebrated Microsoft tools like SLAM, and they got the bugs fixed by the people in the kernel team. And so I thought that this is really awesome for academic research, right? I came from theory, denotational semantics, and here we are getting bugs fixed by the Windows kernel team. Awesome. So I thought that this was really great, but then, oh, that's the kind of data structure we found in one of the device drivers. The Microsoft FireWire device driver was 5 cyclic linked lists, 3 of which had an acyclic sublist. And so we had to have an accurate program analysis for that. And it wasn't too easy. And so we succeeded. So I thought it was awesome. But then um, I'm sitting in a cafe in the East End of London with my collaborators. There's Yang and DeStefano and Calcagno. Calcagno was here. Um, and in this cafe, Calcagno said, "These results are completely useless. This is ridiculous." And I said, "Well, what do you mean? I mean, this is obviously at the absolute leading edge of academic research, right? This does a little bit better what the celebrated tools like SLAM were doing." He says, "How many companies are going to have a lot of discrete 10,000 line programs that you can apply these problems to? Not many companies, maybe one, maybe Microsoft." So you see, Calcagno wanted to make a company to market this stuff. He didn't want to merely get to the edge of the academic research. He wanted to make a company, so he said this is useless. So this was really an eye-opener for me, and it should be for academics. What the things we aim for very often, you can get to the edge of the academic research, but you should ask yourself, is that an end? in and of itself. In this case, my collaborator Calcagno said, no, that's not an end in and of itself. And so I was taken aback. After recovering, I said, well, what is it you want, Cristiano? And he says, we need to go for big code. We need millions of lines of code. And he said, what is the main blocker stopping these advanced program analysis techniques from applying to millions of lines of code? I knew immediately. They need preconditions. They need humans to give me preconditions. And this makes for a global program analysis that will never scale. So in any case, this is the only little bit of logic that you're going to see in this talk. Um, so we made a program analysis which uses the notion of abductive inference, which you might have heard of, which is inference of hypotheses. We used abductive inference to guess preconditions for procedures. And this is just a little bit of it there. So in this bit of code, we've got a spec for foo, which takes two separate linked lists. That's the only bit of separation logic we will see. Two separate linked lists and gives me back a linked list. Um, then after malloc malloc, we call foo. Now I've got x is, well, that's a linked list of length 1, and I've got z, but you see my precondition needs a list x and it needs a list y. We're missing something. And so what we do is we call what's called a biabductive theorem prover. You see at the bottom the list y. The theorem prover doesn't just say yes or no, it discovers the list y at the bottom, and it discovers the z points to nil at the bottom as well. So it discovers the z points to nil. That's the bit that's unchanged by the call to foo. That's an artificial intelligence problem called the frame problem that you need to solve. The other one is the abduction problem. That's Cristiano mainly did the frame inference. Dino mainly did the abductive inference. In any case, we use the abductive theorem prover to guess. We do symbolic execution of a program. We use abduction to guess what the preconditions should be, and eventually we get a postcondition. Um, that's sort of as technical as we're going to get. But the upshot is, by using this abduction technique, we were able to move from 10,000 lines of code to very big programs. Um, it gives you a compositional program analysis technique where you can analyze the procedures independently of one another. I mean, modulo some things about recursion. Um, but you see, things get grouped together as well. You can get after interprocedural bugs. But you don't end up verifying all of the code because, well, maybe there's a bug in part of the code, or maybe your abstract domain is what we talk about in program. Your abstract domain might be not smart enough to verify the entire program. By the way, like if you give me Linux, there's nobody's ever made an abstract domain that's smart enough to verify Linux to the parts of Linux that don't have any bugs. So the compositional approach is very tolerant to imprecision. So this is good, and it scales very well. Um, and so where we had the Cav 08 paper, where we could deal with 10,000 lines of code, moving on to Popolo 09 paper, we can deal with millions of lines of code because of this thing going for preconditions. And the interesting thing is we did that because Calcagno reacted and he said, although this was the edge of the academic research, it wasn't good enough because it won't let me apply to big code. So applying to big code is what brings us now to the next part of the talk. I'm going to talk about our experience with the Infer program analyzer at Facebook. So we were academics. The difference between doing the whole program analysis on 10,000 lines of code and doing the abductive analysis on millions of lines of code is that you can make a company based on it. And we did make a company based on it. And some folks inside Facebook saw that this had some potential, and so they acquired our company. So now we go work for Facebook, and this was sort of realizing Calcagno's idea that we had to go for big code in order to make it real. But okay, so that's all well and good. Should we go for big code? That sounds good. So nonetheless, once we landed in the company, talk about a culture shock for people coming from program verification. Program verification. Let's make up a slogan for that subject. Move slow and break almost nothing, right? Let's write specs, let's write proofs, let's do that. We land and we find move fast and break things and things like this, right? You might think this is the worst possible situation for people coming from program verification. I'm going to try to argue in this talk, though, that actually, once you understand these things right, there's a great situation for deploying ideas from program verification. And if only the academic community would um, start moving a bit faster, they'd have an opportunity to have a lot more impact. Um, so just to give you an idea, so you might think program verification people will land in a company like that. Let's change their programming culture, right? Let's teach them how to program. Well, that's not really going to work. You know what? This was from last year. There's 100,000 commits, Git or Mercurial commits per week to the code bases, right? Um, this thing is not only is it big code, it's huge momentum, right? It's moving fast and it's big. And I'm not going to come in with some unproven philosophy of program verification and change that. So I think a better idea is for us more academic people to adapt to that sort of situation. Um, so we land, and then we've got a program analyzer. Um, I'll tell you what it works for later. It works for Objective-C, and it works for Java, and we're running it on mobile apps. So we've got a program analyzer, and we hook it up to the internal Facebook infrastructure, and then we say, now we've got to deploy, right? So this wasn't our end goal, but first we said, or I had this idea, you know what I've heard from the academics especially, um, false positives are the most important problem in program analysis. So we worked, and we filtered, and we tried to get that false positive rate down. And I sort of thought it was probably like 20, 15% or something like that false positive rate when we deployed. And what we did is we would run it nightly, take millions of lines of code, take several hours, make a bug list, and then assign the bugs to developers. And what happened was nobody congratulated us for our low false positive rate. Um, the bugs would sit there and not get acted upon, and I was very puzzled, thinking, I mean, what are we going to do here? And I tried to understand this, and I went around the company and I was asking people, and they were giggling at me because they knew that this is like the really wrong idea for how to deploy anything. Um, but let me give you some examples of why that is. Um, the most important part is context, the human cost of context switching. So when you're doing a proof, I'll speak to the academics, when you're doing a proof, right, and somebody brings you one of your old proofs even from a year back, and they ask you a detailed question about that proof, you need to context switch out of your proof, context switch in the old proof. I mean, it's hard, right? And it's quite irritating if people are coming at you and they're not sure there's bugs in your old proofs, right? It's a big cost of context switching. Same thing in software development. I'm working on some code. Somebody brings me some code that I worked on a year ago, and maybe there's a problem. It's pretty difficult to context switch back in, right? So context switching is hard. It's even hard to figure out who to assign the bugs to. So this deployment model didn't work very well. Luckily, we had this compositional program analysis that I showed you before, which if I change a little bit of the program, I can reanalyze just that little bit of the program like you do with a compiler. Um, and this fits beautifully with the way the programmers work, their workflow. So the way the programmers are working is programmers submit code at Facebook. Then there's a code review system. There's like a social network for code called Fabricator. And then other people, the reviewers and the coder, will talk about the code, and eventually the code will be changed and changed and changed and accepted. So there's a conversation going on. So our program analysis participates in that conversation. And so the way it works is the developer submits a code change. Then there's something called the continuous integration system. Code reviewers are discussing the code. Program Analyzer runs in the data center. Program Analyzer is running in the data center, um, and gets the code reviewers are discussing. Program Analyzer sends bugs on that code change, not the entire code base at that moment. You see, this gets a long way to solving the context problem, right? Everything is in context when the developer gets that information. So we've gone some way to solving a big part of that human problem. The other thing is it needs to run fast. They're going to commit their code They're moving fast. We need to get the information back to them within 30 minutes or so. Millions of lines of code base, but small code changes. We need the information back in 30 minutes or so. Better in 10 minutes, or it'll be too late. But um, so what happens is there's code and automatic comments are written on the code. Like there's a potential nullity reference here. Automatic comments are written on the code by the program analysis tool as it's running in the data center. And eventually everybody's happy and the code gets shipped to production. This made an unbelievably huge difference, right? When we made the original deployment, then hardly any of the bugs get acted upon, and was chasing people trying to get them to act on the bugs. Now, all of a sudden, hundreds of bugs are getting fixed every month. Hundreds of bugs are getting fixed because it's just there in the workflow. Unbelievable difference. Um, so this moving fast bit, you can't overemphasize how important it is for program verification and analysis to move fast. Um, Here's an example. The developers feed back to us. They're happy because it's moving fast. It gives a way better experience. On the other hand, what about breaking things? So here's one of these things again. Oops, a false positive. So one of the developers is commenting to me in a messenger chat. Um, Oops, there's a false positive there. And I said, oh, that's pretty subtle. Now you're worried, right? As your static analysis developer, oh, I've committed a faux pas. At this point, we've made a false positive. But then the developer says, you saved me trouble other times by seeing these NPEs, and thanks for the tool. So it's interesting working inside the company. The developers are moving fast and they're incredibly positive. They just don't want us to slow them down. Our tools need to move very fast. Um, and the interesting thing there is we used to be so scared of false positives we would never ship a check until we were sure. We thought the false positive rate was low. Not sure, we thought. Um, Now we ship them earlier and get feedback from developers and make it better. So we develop the infer static analyzer in an iterative fashion, same way as many products in this internet age are developed. Um, so we're less scared of false positives, and the the developers will accept us breaking things as long as we move fast. And this is really a key for making static analysis more widely used in the real world. Okay, so let's look at a couple examples. Right. How many people here have programmed in Objective-C? That's a lot more than a purely academic conference, let me tell you. So, does anybody see a problem with this code? Oh, you should, because there's something at the bottom. Okay, Objective-C doesn't use the normal, I can't remember the jargon, but there's a garbage collector which can collect cycles as well as non-cycles. Um, Objective-C uses reference counting. And the problem with reference counting, of course, is when there are cycles in the garbage, it doesn't get collected necessarily. Um, Now, in Objective-C, so you've got this problem, but it turns out that this problem comes up in practice almost always in conjunction with lambdas. So this up arrow is a lambda in Objective-C. Um, One of our people, Stefano, talked to some of the Facebook developers, and they said, this is the main problem in Objective-C that causes us pain. And so he made a check, um, and so it finds this retain cycle. So here, little c gets allocated, and then c dot handler is equals this lambda expression. The lambda expression at runtime creates a closure, right, another object, and it's got a reference to c within it. So there's your cycle, and then they go to scope, and so that's what's called a retain cycle. So the interesting thing is this actually, it's a small example, but it needs some somewhat advanced program analysis. It needs shape analysis, cyclic versus acyclic structures it needs to distinguish, and a little bit of lambda, right? So it needs, so was the main thing, the first thing the Objective-C programmers at Facebook told us to get after. Um, Here's another example of the kind of thing you come up against. So I'm not going to show you Facebook code, but oh, here's a funny one. So when there was the heartbleed problem, um, Infer program analyzer did not find the heartbleed bug. Like many other static analysis teams, we implemented something which then would find the heartbleed bug. But that's too late, right? I mean, we just have to admit that that's too late. So we didn't take any credit for that. But we did run Infer on OpenSSL at that point, and we found some bugs. And we submitted 15 of them to OpenSSL, and OpenSSL fixed them. Here was one of the easier ones, but it's deceptively easy. Um, so there's a malloc, and then there's a dereference, and so malloc might have returned null. Except that this is what you run into when you're doing program analysis in the real world. OpenSSL malloc isn't malloc, it's a wrapper for malloc. And it's this wrapper. And so what is the program analyzer had to do to understand this? It had to first analyze this procedure, find pre-post specs, using that thing that I told you before, and then it had to use those pre-post specs um, to analyze this procedure. And by the way, it had to go and analyze the other procedure, buff, string, and copy, to find that's where the bug is. So you see, this is the simple looking thing, and quite sophisticated interprocedural program analysis has to be done to catch it. Um, many of the null bugs we come across are interprocedural of this variety. Um, now, here's another example. Um, so what, Infer has been open sourced. So that was a C example. This is a Java example. Um, this is so Google has the Garrett code review system. And so this is something they use for code review, and they've open sourced it. And we ran Infer on it, and Infer has inside of it what's called a taint analysis. And it found this problem. And it reports it like that. Tainted value reaching sensitive function. There's something, let me say this, something which could be vulnerable to a man in the middle of the attack. SSL socket was not verified. There's a point I want to make about this example. Um, Two of our engineers found this example by running it on Garrett. So this is Sam Blackshear and Jules Villard. Um, they stared at this potential bug for hours. Might have been over 10 hours. And they were trying to figure out, is this a real bug or not? And they couldn't figure it out. So then they talked to some security experts in Facebook who've worked on this sort of thing. Is this a real bug or not? Not sure, but it looks like I'd be careful about that. Submitted it to the Google folks, and the Googlers, they didn't tell us whether they said it was a real bug or not, but they fixed it. Okay? But there's a serious point that I want to make here. And that's this. One of the main things I've learned is that there's a concept of false positive, and it's a good concept. False positive would mean if I happen to have a complete program, um, and I report a bug at a certain line, then that bug will occur. That's a true bug. If it can't occur, it's false positive. I have no problem with that concept, but the false positive rate is a very difficult concept. And it's a very difficult concept because it's essentially unknowable. Humans don't know. The experts, like in this Garrett bug, aren't sure whether that's a true bug or a false positive. Many of the things that the static analyzer reports, Infer reports, are in between. So maybe it's a true bug, but the human doesn't know even after looking at it for a long time. Furthermore, this is worse. We have code bases in the millions of lines that are changing at an incredibly fast rate. Humans can't keep track of that and figure out the false positive rate. So this concept of false positive rate is something that, to my way of thinking, it's not measurable. So it's an okay as a sort of abstract concept. It's not, you can't, it's good for a measure to be measurable. And false positive rate is not measurable. So I think the false positive concept is not useless, but the importance of it is completely overestimated in the academic community. And in industry, what I've really learned is it's evidence-based. We like to measure. We like to measure more than I ever did as an academic. There's something I can measure, and I can measure the fix rate, the rate at which the warnings by the static analyzer get fixed by the developers. When we open sourced Infer, we reported there was a fix rate as we had measured it around 80%. That changes over time. We've seen it dip into the 70s. We've seen it dip into the 60s, but the important thing there is compared to the batch mode deployment where the fix rates, you can have a same program analysis, deploy it in batch mode or deploy it incrementally and have radically different fix rates, right? So fix rate is more measurable. it speaks to something to the value that the analysis is bringing to the programmers. So, in all, it's a better concept than false positive rate, or it's more useful to the analysis developer. So we track that. Um, we track, of course, you have to retrack the report volume. Um, one more thing I want to mention, the things that we track. The other thing I've learned going into the industry is the importance of performance is much more than I had realized. Our team spends a good amount of its time working on perf. You saw the earlier chart I showed you where our analyzer was running on millions of lines of code. Um, as academics, our analyzer was amongst the most performant program analyzers one would have ever seen in the academic world. But we're always fighting against perf. We need to get more perf to get feedback back to the developers more quickly. And some of the main problems we've had, so there's differential perf. Not only do you care about perf on the entire project, but on code changes. You need quick answers on code changes. Even a linear time algorithm, if only working on an entire code base, is going to be too slow. But many of the problems we faced have to do with perf. And so this was an example of one of the problems we faced where we were chasing more and more bugs for Objective-C analysis. And this is the amount of capacity Infer was taking in just some portion of the Facebook data centers. This was creeping up, you see, as we were chasing more and more bugs, until it was decided that you guys are taking too much, you people are taking too much capacity. And so we actually had to switch it off for a bit and then get our perf under control. Biggest problem, even though we had the most performant academic program analysis, one of the biggest problems we faced internally is perf. So, so program analysis needs to go faster and faster and faster. Um, we spend a lot. We spend a lot of time working on perf. Okay, so what's the status of Infer right now? So inside of Facebook, it runs on every diff or every code mod for the iOS and Android apps for Facebook, Messenger, Instagram, and WhatsApp, right? And so there's lots of code, and that code's used by a lot of people, so that's good. Hundreds of bugs are reported by Infer each month and fixed before they reach production. Um, it uses, yes, a custom separation logic theorem prover, but it also uses, I mean, I'll say the words abstract interpretation. We've got various abstract domains. We use whatever we can, and there's lots of good ideas from abstract interpretation to use, and we do. We use them. Um, besides being used internally, we've launched it to the open source, and it's used by several other companies like Spotify and Uber, who've contributed back to it and it helped make it better. Uber, it runs on every diff at Uber as well. Uber has a similar software development model to Facebook. Um, so because we open sourced it, so friends in the community get to use it, so individuals, not just companies. So this person, Smedley, thinks that Infer is badass, so we have no reason to quarrel with Smedley there. Um, so, so lots of people have fixed bugs. Another thing a bit different from working in academia is you end up with things like this. There's I think that's a Wired article, or AI tool is smashing bugs is now open to all. Um, so this is a conference where we hear a lot about functional programming, right? So you might ask me, have you run Infer on itself? Well, no, not yet. I work inside of a company where there's lots of ardent functional programmers, including on our team. So this was when we open sourced Infer, there was a Hacker News thread, right? And in the Hacker News thread, I'll just read it. Legend has it there's a small room at Facebook headquarters containing a quorum of OCaml committers, all in French for some reason, hacking away at a level of abstraction beyond the ken of mortal man. Um, so yes, Infer is written in OCaml, and one of the members of the team, Jules Villard, is French, and he responded to this thread with this one. So that's a lot of fun. Um, okay, but to get a bit more serious, what I really want to say is that um, there's been a tremendous amount of work on program verification and analysis in academia, and it felt like it was a well-developed subject. When I moved to industry, I think the work is there's a lot of really, really good work, yeah? But it feels like from an engineering point of view, the work is very underdeveloped. Um, so by that I mean when we're developing our tool and trying to make it go fast at scale, we're having to make algorithmic decisions in territory that nobody's ever been before, and we can't find anything in the academic literature to help us. And so we don't necessarily publish the papers to pause to publish the papers, but it's not that we're flying blind. It seems like doing program verification for toy little programs, there's been a lot of that. Doing it at scale and at speed has hardly been done. There's not much to find out there. So maybe I can turn this around and I can say that I think there's a tremendous amount of impact being left on the table by academic work in program analysis. And the more we can concentrate on compositional analyses that go fast, the more we can open the door to more impact and, well, just make the world software better. So, okay, that's a good place for me to stop. Thank you.
So I'm not familiar with Fabricator, but it looks sort of like Git pull requests or something like on Garrett, where it's line-based, where you can leave comments in certain lines. Can you talk about how you, or what possible issues you've run into trying to explain the results of an interprocedural analysis using just commenting on single lines? Do you have developers who have trouble understanding why the tool reached the conclusion it
This
did?
is where they've surprised us as well. So we have something which a link they can click to go see an interprocedural error trace. But the nice thing is we measure at Facebook, so we measure how often do they click that. Not often. Way less than 5% of the time. And what we found is that, let me joke about the concept of abstract interpretation. So there's this error trace, then what we try to do is to give an English explanation, which is, quotes, an abstract interpretation, the best English abstract interpretation of that error trace that we can give, which gives the reason. And we've fiddled with those over time. And usually the developers, they can read that and they can understand it on the spot, even though it's interprocedural, and they might go look at it. And getting the developers to react quickly, um, having the good error message counts. So for instance, for a null pointer dereference, we say the null was created in that procedure and returned here, and dereferenced here or dereferenced in the other procedure. They probably know enough. They probably know enough about the surrounding code to, you're right there, and I can see how that all fits together. And the developers are making the decisions very quickly. So not often do they follow those interprocedural traces, surprisingly.
Thanks
Hi.
for the nice talk. Oh, currency issues.
No, just go for
All
it.
right. Thanks for a nice talk. So I was wondering what kind of techniques you use to get performance. So you mentioned compositional analysis. Is there any other technique that you applied successfully?
Well, yeah, there's lots of things. I mean, there's like typical abstract interpretation things like join, which means to not have as many um, choice points. Listen, there's once you start applying things at this scale, there's unbelievable amounts of fat in various parts of the analysis. So just by the typical things engineers do of profiling, we can find lots of fat to get rid of. Um, we've got some novel program analysis algorithms which schedule things in different orders, which, I mean, we're going to talk about later. So there's some novel program analysis algorithms that are actually going on, which I hope we'll talk about more at another time. But um, yes, so there is stuff, but not stuff that this quickly I can explain that well.
So my question is surrounding the kind of problems that you're trying to solve are all related to the kind of imperative style that is proposed by both iOS and Android, where you have the referencing, you have these loops and all that stuff. Um, why is Facebook trying to solve those problems kind of with a static analysis rather than into moving into a different paradigm where no pointer exception is not the default way of returning a method that
Well,
has a less
yeah, so that's very interesting, isn't it? I mean, uh, so you've got things like, I mean, Apple gives us iOS and Google gives us Java, right, for Android, and then, I mean, that's not in our control. So we have to deal with that. So I love things like ML, right? And there are no null pointer exceptions in ML. And if the whole world programmed in ML, that would be cool with me. I mean, there's lots of problems, even in ML. Um, but we should respect the industry. I mean, to say things like, um, oh, just change your programming language and then all of these problems will go away. A lot of other stuff comes along with it, like the libraries, just a lot of other things. And so, I mean, it will take some time for some of these technologies to be proven to the extent that they can get wider acceptance. Um, and I think we should just respect the industry problems, and I'm just there to help them. And if there's languages like ML get wide acceptance, I can find analysis problems in ML too, especially surrounding concurrency. So, but I think academia, let's not put our heads in the sand and say, oh, if only these industrialists would change their language. I mean, they're actually thinking very carefully about the language, but also the programming environment. And they make very serious decisions about which ones they use. So.
Okay, so will you still be able to finish this job if you were still working on academia?
I'm sorry.
Will you still be able to finish this work if you were still working on the academia?
In academia, we got it to the point where it was pretty good. Um, Now we've got it to the point where it's a lot better and it's deployed. No, because to take the leading edge popular cav paper, turn that into something that can be deployed in industry is more than 10x extra work, much more than 10x. So, no, I don't think we could have done it.
Do you have an internal deadline for C++ support?
How do I say this? Watch this space. Some C++ is coming. I'm not giving you a date.
Does your 99% left include functional specifications?
This is a very interesting question. I mean, a program verification person is like, if only they would write the specs, I can do so much. But think of this. Suppose we had the perfect verification system that instantly gave us the right answers. How do we deploy that to the world? It's very hard to deploy that. So, I mean, it's included in what I would love to do, and certainly in that 99%, but we shouldn't kid ourselves about how difficult it is. And the great difficulty is not making a good program verifier. The great difficulty is figuring out situations where this brings high value to the programmers and convincing them of it. Well, there's education too. So yes, and that's my longer answer as well.
Are privacy issues not part, would they not have been addressed with functional specifications?
Well, for instance, yeah, sure. I love functional specifications. The hard problem is getting the people to write them, not to verify them. So.
So at work we use Flow for JavaScript.
Who's?
Sorry.
Oh yeah. Okay.
Yeah.
Yeah. Cool.
We use Flow for JavaScript code base.
Yeah.
Can you talk about how Flow and Infer differ?
Yeah, I love Flow. So Flow can get rid of all null pointer exceptions, I think, by typing. Is an example of what it can do. It's like ML for JavaScript, ML typing for JavaScript. So the difference is that Infer has Infer can be used more easily. You can just drop the code into Infer. Um, Flow, you have to interact with it, but when you interact with it, you get more. Like Flow is an example, like Sophia asked the question about functional specs. Types are the sort of easiest, simplest version of functional specs. Flow has that. And so you can get more, there's more friction with Flow. Less friction with Infer, but you can get more out of the Flow model. I'm in sort of in favor of program analysis where it's like Infer, completely automatic, but where you can sprinkle in types and give you more. And so the way these tools tend to be is it's like one or the other, and there's no reason for them to be one or the other. So Flow and Infer are sort of two ends of the spectrum there. I would hope that, I mean, going forward, we can have Flow Infers, like, if you see what I mean, yeah?
Cool. So I had a question. I think this is super awesome coming from industry and also being like seeing the horrors of like non-testing that happens. I was interested in when you said perf. What actually mattered most at Facebook? Was it resource consumption or was it speed? So like
Both.
both.
So
Okay.
this diagram I showed you
Yeah.
was resource consumption. We used up too much of part of the data center, and this is bad. Um, so this costs money, and it stops other people from doing things. So that's bad. But also, if infer runs slowly, then while all of the people are commenting on the diffs, hey, I think you've got a bug there, then infer is too late, then they're not going to pay attention to it. So it needs to get in there in, say, 30 minutes tops as an average, or better, less. So anytime we've got a regression that slows infer down, that's bad, right? That will lead to a worse fix rate. Um, but anytime we take more of the data center, that's bad. That costs too much money. So both.
And then I had one more, if that's okay. So you're using the work that's come out of Microsoft in terms of like Iron Fleet and the Daphne language. And do you guys have any thoughts? So the idea there is they're trying to almost embed it in the IDE and then have it running background in the cloud. Have you guys looked at doing that? I mean, that seems incredibly resource intensive.
It looks really cool. It looks really cool. But I'm not sure I understand the exact names of the tools, but the work coming from Microsoft in that direction, I think this is like to Sophia's point. The question is how to have it deployed.
Yeah.
So the problem is like we can create this so researchers can use it to make demos, but we need to create this technology so that practicing software developers use it. And for that kind of technology, that's the problem that needs to be overcome.
Yeah. Um, have you got any interesting insights to language designers besides be like ML? Like,
Yeah, of course I do. But I mean, being like ML is a great first step, right? Um,
but for more imperative, like
yeah, I mean, probably you might have heard of concurrent separation logic. Some of you might have heard of it. And this gives us a brilliant way to type check concurrent programs. And there are even languages like asynchronous liquid separation types and Mezzo, and it's related to Rust. Yeah, so there's lots of stuff can be done with concurrency, and we're only scratching the surface for language design and typing for concurrency. That's an example. So
Can you comment how you hook into the compilers? Like, are you making use of compiler interfaces? Are the compilers providing the right interface for you to parse the different languages, or are you writing your own parsers?
right, we're writing our own parsers or using other parsers, so we don't just hook into the compiler. What we do is we hook into the build system, and we intercept calls to the compiler. So one reason why it's 10x, it costs you 10x or a lot more, is because, okay, so we've got Maven and and Buck and various other build systems for Android. Infer needs to work with all of them. Make needs to work with Make. So if I want to run Infer, if I can go Java C blah blah blah, then I can just infer minus minus and then build command. Infer minus minus Maven blah blah blah, and so then it just goes. So some people can run it out of the box. So not so much we interface with the compilers, but the build systems is huge, hugely important.
Sorry, but just to follow on, then I understand interfacing into the build system, but then you're getting like each of the codes from the compiler. So what intermediate representation, like what are you pulling out from that compilation?
Well, I mean, so we're doing it differently in the C family of languages and the Java family of languages. But what we do is you have to take the source, you have to get it into some. We have our own intermediate language. It might be called the Smallfoot intermediate language, and it's we compile all of our languages into that. Then we analyze the Smallfoot intermediate language. It's a intermediate language oriented to the kind of program analysis that we do. Okay.
Thanks very much.
Do you want a t-shirt at any point? Or
No, I'm okay for
good. Just wondering.
Was there the thing? Oh, that's yours. Okay. All right.
So I thought that this is really awesome for academic research, right? I came from theory, denotational semantics, and here we are getting bugs fixed by the Windows kernel team. Awesome. So I thought that this was really great, but then, oh, that's the kind of data structure we found in one of the device drivers. The Microsoft FireWire device driver was 5 cyclic linked lists, 3 of which had an acyclic sublist. And so we had to have an accurate program analysis for that. And it wasn't too easy. And so we succeeded. So I thought it was awesome. But then um, I'm sitting in a cafe in the East End of London with my collaborators. There's Yang and Di Stefano and Calcagno. Calcagno was here. Um, and in this cafe, Calcagno said, "These results are completely useless. This is ridiculous." And I said, "Well, what do you mean? I mean, this is obviously at the absolute leading edge of academic research, right? Um, this does a little bit better what the celebrated tools like SLAM were doing." He says, "How many companies?" So, yeah. Okay, hello, let's get started. Right, so um, I love the idea of this conference. It's about academia and industry needs to talk. So a bit about me. Um, I'm working for Facebook now on static program analysis, but I came from academia. I was a professor for like 20. Gotcha.
Good to go. Is the mic on?
Hello? I think we found some bugs in the code, and then when we fixed the bugs, our program analysis confirmed that there were no bugs left, right? So it verified the code. Um, I thought this was this. I love this. I thought this is awesome, right? So a bit about my background. I came from denotational semantics, then I did logics of programs, and somehow I got dragged into doing static analysis, and finally I'm doing static analysis in industry. Well, this was at the leading edge of academic research in static analysis and program verification of around 2008. So at that time, program verification was going through a renaissance because of SLAM and Astray and certain tools which you would call verification-oriented abstract interpreters. And so a great thing about this work is that, right, so we found a bunch of bugs. Two of our collaborators on this paper, Burdine and Cook, were working at Microsoft at the time. These bugs were missed by the celebrated Microsoft tools like SLAM, and they got the bugs fixed by the people in the kernel team, and years or 22 years before joining Facebook. And so what I'm going to do in this talk is I'm going to get to the Facebook part, deploying program analysis, but I'm going to go back a bit before that to some of the academic work we did, and I'm going to talk about some of the sort of weird and wonderful things we've learned trying to take some academic research and apply it in this industrial setting. So let's go back in time a little bit. So we're working on program verification or static analysis. Um, we had a paper in the Computer-Aided Verification Conference in 2008, the CAV conference, where what we were trying to do is make a program analysis which takes in a program and tries to prove that it has pointer safety or memory safety. So there are no pointer dereferences, no memory leaks, things like that. And in order to do this, you had to do something called a shape analysis. So we wrote this paper, and the largest programs we were handling were around 10,000 lines of code. This was C code.